Welcome back, second day of energy. Today we're talking, well, actually, raise your hand if you remember from last year the difference between a conservative force and a non-conservative force. Hands down. Raise your hand if you have any idea of these words of which I am speaking. Not really, right?
Oh wait, I meant no, I don't have any idea.
Good job. Thanks. All right. So clearly the word conservative versus the word non-conservative does not ring a bell. And for good reason. Because last year, it was an afterthought. But no one even remembers even hearing those words uttered by your physics teacher. No. Conservative versus non-conservative? All right. I thought that might have been on a couple of AP Physics B multiple choice questions, maybe. But all right. So, the definition is entirely new to you, apparently. Conservative forces, things like gravity, electrostatic. What's the only non-conservative force you see in the list there?
Friction.
Friction. Okay. All right. So, So, bearing in mind that no one has ever even heard of those descriptions before, let's go take a field trip to the back of the room. All right, so what I want you to do is we have a cleverly constructed grid on the ground, and I'm going to need some help doing this. What we're going to do is we're going to lay out these sticks every 2 feet pointing down. So like every intersection pointing down. All right? And we're going to do it, and we're going to make actually a field of these sticks pointing down every 2 feet. All right? So continue that pattern. All right. So what these sticks are, they're all pointing down, which they're representing gravity. It's basically we're creating a gravitational field. What way does gravity always point? Down. Now, does gravity get any stronger or weaker where you are? Not really.
Well, if you're in space.
Not really. No, the little g is... You know, here near the surface of Earth, it's pretty steady. Actually, let's put these up right at the 2 feet point, so they're all exactly the same. So what we've created is a fairly uniform, except for the fact that it's missing some sticks, gravitational field in this area of the room. All right. So now, what way is the field always pointing? Down. All right. Okay, so, yeah, quality control. All right, so everybody point with your finger which direction is down in this room. Okay, down is towards me, or towards that wall anyway. All right, so let me see. If I were to start here, and let's say every 2 squares is 1 meter. It's not, but let's pretend like it is. And we're also going to pretend like that way is down. All right? And I have a mass of 1 kilogram. All right, so I'm a pretty lightweight guy. All right, I've got a mass of 1 kilogram. If I were to move from here to here, how much work did gravity do on me?
1.
Yeah. It'd be the force times the distance, right? What was the force on me? mg, which is 9.8 newtons. And what was the distance I moved? 1 meter. So the total work that gravity did on me, 9.8 joules. Okay, what if I go from here to here? 19.6 joules. All right. What if I went from here all the way, 1, 2, 3, from here to here?
28.4.
29.
Math.
29.4, right? Okay. So what if I did that in reverse? What if I did like this? I did 1, 2, 3, from there to here. Gravity did negative 29.4 joules of work on me. Wouldn't you agree? All right. So I'm going to start here again, and I'm going to do something real tricky. You ready? I want to know how much work gravity is doing for me from here to here.
Oh no.
Why 9.8? Did I move farther?
Yes, but when you're acting perpendicular to the force of gravity, you're no longer.
Ah.
Work is no longer.
Yeah, because the horizontal doesn't matter, right? All right. So what if I start here and I go here diagonally?
Another 9.8.
Still 9.8. How come?
Because the right direction.
Yeah, the horizontal doesn't matter, right? Because if you do the cosine of 45, even though the distance was square root 2 meters times cosine of 5, it's still just 1 meter that way. Does that make sense?
Yes.
All right, so that's how the whole dot product thing works that we were talking about yesterday. All right? All that matters in this case is how much vertical you're going, not how much horizontal you're going. Okay, fine. What if I did something like, I'm gonna take a little trip. You ready? Here we go. I'm gonna start over here. I'm gonna walk this way, and then I'm gonna do a little jig and circle, and then here, back to here.
Zero.
Well, how zero?
Because you're doing the path doesn't matter.
The path doesn't matter. Oh my God, the path doesn't matter. I did the same amount of work. It doesn't matter what I did. I ended at the same spot. The total work was zero. The path doesn't matter. And that, my friends, is the definition of a conservative force. It is a force, if you have a force field for a conservative force, it doesn't matter which path you take. You'll always end up at zero total work done by that force if you end up in the same spot. Or there's kind of a converse way to do it. What if I want to walk all the way to that corner? What if I walk like this? All right, and end here. How many joules of work did gravity do on me? 1, 2, 3. 29.4 joules. What if I did it like this? 29.4. The path doesn't matter, right?
But if it's friction.
Ah! Is it possible? Is it possible to create a force field, to arrange these sticks in such a way that the path that you take does matter? Do it.
But if we point them all outwards, then if you go like,
in the direction that he's going.
yeah, it just has to follow him. Like,
It has to be like magnetically arranged towards your direction.
yeah, just follow you.
How would you arrange these sticks in such a way
wait.
that the direction I took to get back to where I started
now walk.
would matter?
Okay, now walk.
Yeah, I would.
Oh, you're saying there's no force field over here and there is over there?
Okay,
now walk.
Oh, I like it. So what you're going to do is you're going to create a force field that does what? That follows me.
Goes against you.
Okay, go ahead. It's just a cheap way of having
Are you
it.
pulling?
Okay. Are you going to point?
Yeah.
Okay, so what he's doing is he's going to create a field that points backwards from whatever direction I'm going. All right, you ready? Okay.
Nate, do it from the front.
No, like push, like point towards him. 'Cause you're pushing.
No, I'm not.
Oh, a field that pushes me in whatever direction I'm going. Okay, so how much force is this going to be? Give me a number.
Mu to n.
Oh, that's a complicated number. How about 1.
1. Okay.
Okay, I like that force.
Wait, I
Okay.
Yeah, you told me 50.
Okay, so which way is the force going to point?
This way.
Backward. Okay, ready? Here we go. So the force is going to be 1 opposite the way I'm going. Okay, ready? Here we go. And I'm going to walk to that corner. Ready?
Yeah.
1 meter, 2 meter, 3 meters, 4 meters, 5 meters, 6 meters, 7 meters, 8 meters, 9 meters, 10 meters, 11 meters, 12 meters. All right. So nicely done. So how much work did that force do on me?
Like 13.
The force
It
times
did.
the distance.
98.
The distance.
No, the force was 1
Oh,
backward.
just kidding.
So how much work did that force do on me?
7, 8, 9, 10. 10.
Negative 10. Right? Because it was pointing backwards. What if instead of walking along that path, I started here
I don't think you're gonna make it.
and I went straight there? All right, here we go. Here we go. Here we go. Going this way, going this way, going there.
Close enough.
So how much work did that force do on me?
7.
7. Okay, so that did negative 7 joules. So did the path matter?
Yeah.
What kind of force were you simulating?
A non-shape.
A friction force, right? Is friction force conservative?
No.
No, nicely done. All right, so because the path matters. There are, by the way, friction is kind of a weird one because it depends on how the body is moving, right? Could you create a force field, a permanent field on the ground that would be a non-conservative field?
Tornado.
Do it.
No. Have all the sticks pointing outward.
What?
Yeah, circle almost.
Okay, so which way are these sticks pointing? Are they pointing clockwise or are they pointing counterclockwise?
Clockwise.
Clockwise. So they're pointing this way. So if each stick is going to be a 1 Newton force and they're 1 meter apart, okay, so if I walk this way, okay, so I'm going to start here. I'm going to go around in a circle. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
What? Oh, man.
What does that one do?
Let's get rid of that one. Yeah, field lines cannot cross. You know why?
Oh.
Why can't field lines cross?
It's not the same force.
Oh, 'cause it's not
if
field.
it's crossing itself.
That means there are 2 field directions in one location, and that's physically impossible.
Oh.
Right? You can't have the force be in 2 directions at once. It's got to be in a direction. Okay, so how many joules was it for me to, how many joules of work did the field do on me walking around that way?
0.
Darn.
Oh.
No.
What?
1, 2, 3, 4, 5 joules, 6, 7 joules, 8 joules, 9 joules, 10 joules, 11 joules, 12 joules. Right?
Yeah.
The field is always in the direction of me. So that was 12 joules. What if I walk around this way? -1, -2, -3, -4, -5, -6, -7, -8, -9, -10, -11, -12 joules if I walk the other way. Is this a conservative field? No. I would argue that if you randomly create a mess of sticks on the ground, that the field you're going to create is going to be a non-conservative field. There are only a handful of configurations that are conservative. All the sticks pointing in one direction, down, like gravity, that's a conservative field. But mathematically, in 3 dimensions, the set of conservative fields that you could create is infinitesimally smaller than the set of non-conservative fields that you could create. However, all of the forces that you have dealt with so far, the force due to gravity, force due to spring force, what else? Electrostatic, right? Those are all conservative forces. The fields they create are all conservative. All right? Friction is not a conservative force. What else isn't? Air drag is not a conservative force. All right? There is a third definition of a conservative force. A conservative force is a force for which a potential energy can be defined. Potential energy can be defined. What does that mean? Think of gravity. Is there such thing as gravitational potential energy?
Yes.
Yes. You can define, let's imagine all these sticks were pointing down again, right? You can define a potential energy by saying, okay, this line right here is the zero. And if I go from here to here, gravity did -1 joule of work on me, right? If I go from there to there, it's -2 joules of work. Agree? That means here, if this is the 0 energy spot, this is the 1 joule of potential energy spot. This is the 2 joule of potential energy spot. See how that works?
Yes.
So you're basically, if you have a conservative field, then all that matters is your location in that field. Doesn't matter how you got there or what path you took. So potential energies are defined only for conservative force fields. Does that make sense? So 1 joule, 2 joules, 3 joules, 1 joule, 1 joule, right? Path doesn't matter. And it's only if path doesn't matter that you can have a conservative force and a potential energy. Does that make sense? So what this means is there's a very close relationship between work and potential energy only for conservative forces. Good? All right, good. I'm going to clean up here. Let's take some notes on this. All right, so here we go. We basically came up with 2 different but equivalent definitions of a conservative force. Definition 1 is a force which is path independent, means doesn't matter how you got from point A to point B. Definition 2 is a force for which a potential energy can be defined by where you are. Like, for example, if you're right here and you have a mass of 1 kilogram and you're 1 meter high, what's your gravitational potential energy? 9.8. If you're right here, you're 2 meters high, what's your gravitational potential energy? 19.6. Does it matter how you got from here to there? No. All that matters is your location. Ooh, this is interesting. What way does gravity actually point in this picture?
Down.
It points down. What way does the potential energy gradient go?
Up. Or down.
Huh.
Yeah, down. Yeah, he's right.
Gravity points downhill.
Yeah.
Wouldn't you agree? Gravity points from high potential energy to low potential energy. Raise your hand if you've seen gradients in multivariable.
Wait, no.
We haven't started.
Oh, haven't started. Okay.
Next chapter. Next chapter.
Okay, so this is actually, you're going to see this very soon in multivariable. It's one of the big ideas, and that is force is the slope of the energy. And force points downhill. All right. All right. So we're gonna talk about that. Here we go. So examples. We actually walked this out. 2 different paths: the blue path and the red path. And what do you find if you take both of those paths?
They're equal.
Yeah, they're both -40 joules worth of work due to gravity. All right. Why is it negative work to go up? Shouldn't that be positive work?
No.
Gravity's working
Forward motion.
You're gaining potential energy.
It's negative work because gravity is pointing down. So gravity, the force due to gravity, is doing negative work on you as you're going up. Which means to go up, there must be something else doing positive work to push you up. All right, and that might be the ground or the ladder or whatever you're climbing, right? Yes. All right, here we go. Yeah. Yes. Mr. Bruce, yes. The other guy.
I'm sorry.
Slightly shorter.
I'm not even gonna ask this question now.
But gravity doesn't really do anything, so how come we say it's negative?
Gravity doesn't do
But it's
anything.
not like playing a motor. Well, yeah, it is, but it's not really.
Is gravity a force?
We can't see that.
Does gravity push?
Yeah.
Oh, do you want me to prove that to you?
No.
Oh, you sure?
But if
Hold
it
out your
goes
hand.
Upwards. then
Hold your
how
hand.
come-
Okay. All right. So what I want you to do is
Let it go.
I want you to. I'm going to climb onto your hand. Wait. Got it? All right. So yes, gravity does do something. It pulls things down.
Can you imagine if we just figured out something that's super strength in that moment?
Yeah, it's just the ability to stop gravity. Darn it, my demo didn't work. All right. Okay, here is a random. This is not so random, but we saw it in real life, right? Blue path versus red path. If you go from A to B along the blue path, that field is doing positive work on you. From A to B along the red path, that field is doing negative work on you, which is crazy. But if you were to draw a random field, this is what it would be. All right. Special note, friction. We actually did this. By the way, you were the first person, the first year, to ever come up spontaneously with friction on your own. Like how to model that. Dropping the sticks behind me. That was awesome. All right. Did you get it off in the notes?
Yeah.
Yeah, but I didn't. There's no picture of that in here.
Oh,
It was awesome. It was awesome. It was so cool.
Good job, Nate.
All right. So yeah. So is there such thing as friction potential energy?
No.
Wait. Why not? Isn't friction a force?
Friction's
It's non-conservative force.
It's not a conservative force. There's no such thing as friction potential energy because it's not a conservative force.
It's a liberal force.
Right. Darn those liberal forces.
Oh, that was clever. I think we just got a class catchphrase.
All right. All right. So linking work and potential energy, and this is what I was just getting at a second ago, mentioning the multivariable connection. Oh, no, sorry. Not yet. Work and potential energy is a really simple relationship. The work done by a force field is equal to the negative change in potential energy for a conservative force only. So once again, from yesterday, 1 kilogram mass, I raise it up 1 meter. What was the net work done on this bottle? 0. How come?
Because you pushed it up and gravity pushed it and gravity did work.
Well, I was going to go with the work energy theorem. What's the work energy theorem say?
Oh, there's no change in velocity.
There's no change in velocity from here to here. It's both 0, right? So the net work is 0. But did gravity do work?
Yes.
How much?
Negative.
Negative 9.8 joules. Did I do work?
Yes.
Yes. How much did I do?
9.8.
Positive 9.8 joules. And the net work was 0. Okay. So we say that the work due to gravity is equal to the negative change in potential energy. So if the work due to gravity was negative 9.8 joules, then it gained positive 9.8 joules worth of potential energy. Does that make sense? All right. Same thing works for electrostatics because electrostatic field is also a conservative force. Same thing works with springs. Springs are also a conservative force, assuming it's a 1/2 kx squared type spring. Not all springs are. In fact,
Wait.
no springs are. It's just the model that we use for springs, and it's pretty darn close. It's close enough to work
There are different
for us.
Goes
Sure.
forward.
You can have nonlinear ones.
Oh, my.
Yeah. You have springs, heating up and breaking.
Isn't
Well,
there
that's
like,
not a conservative spring anymore.
isn't there like one element if you like expose the heat, then
Yeah. What if you heat the spring up as you're stretching it?
It will expand more.
Changes the stiffness of it, and then you cool it, and then you let it retract, but it doesn't retract as far. Now you've got a nonlinear spring. It's not conservative anymore. It won't go back to where it started. Good? All right. Okay, force and potential energy. This is the connection I was looking for. F equals negative du over dr. What the heck does that mean? Why are there little arrows on top of the F and the dr? Vectors. Which way does the force vector point?
The way of the
Bah.
Direction of acceleration.
Ah. What if there's no acceleration?
where the field is pointing.
And remember, I'm not talking net force. I'm talking net force equals mass times acceleration. But this isn't net force. This is force for a specific
Oh, wherever
force.
you
Kind of
make a
force.
point.
So force always points downhill. Force always points downhill. The force of gravity points which direction?
Down.
Downhill. The electrostatic force points which direction?
Downhill?
Downhill. What's that mean for electrostatic? Say you have a positive charge and another positive charge.
Towards a lower potential.
This positive charge tries to go where? Away. Well, it turns out that for this positive charge point of view, downhill is away from the other charge. So you could think of it like a big force hill, or a big electrostatic voltage hill. Downhill. Forces always point downhill. All right? Now, this explains one of the most fundamental laws of the universe. Stuff is lazy. Would you rather be standing here or lying down in your bunkie sleeping?
Lying down in my bed.
Why?
I'm lazy.
Why? Why is it so good? Why is it so nap time so good?
Because not moving doesn't require energy.
Because would you rather be up here or down there?
Down there.
It's a fundamental law of the universe.
Well,
Don't deny it.
Sometimes
Anytime your parents are like, "Why are you still sleeping?" You just tell them it's a fundamental law of the universe, and then show them the equation. F equals negative du over dr.
Is that a U?
Yeah, that's a U. So the question is, what's the F?
force.
That's force. What's U?
Potential.
Potential energy. Did you use U last year for potential energy? Raise your hand. Yes, you actually did on the AP test. In regular physics, we didn't use U. We used PE. But U is the same thing as
I
PE.
used
Yeah, we
Oh,
do.
we
Yeah.
we like total energy on like a
Yeah, U is what the AP test uses. So we're going to get used to using U for potential energy. Okay, so U is potential energy. What's the R?
Direction.
Distance.
It's position. It's a position vector. It's your location. Let's see if I've got a better picture of what I mean by all this. Okay, so given the gravitational potential energy scalar field shown below, calculate the force of gravity on an object whose mass is 1 kilogram. And so what I'm basically telling you is here's the height scale, here's the potential energy scale. What is the slope of du over dr? Wait, what's u again? No, what's u again? Energy. What's r again? Height. Right. So what's du over dr if you were to calculate it with these numbers?
19.6 over 2 or 9.8.
So to do a slope, what do you need?
2 points.
You need 2 data points. So you know at 19.6 it's 2 meters, and negative 9.8 it's 1 meter, a negative 1 meter, right? Oh gosh, so difficult. No, let's pick. Okay, we'll pick 2 data points. These 2 data points. We'll pick 19.6 and 2, and 9.8 and 1. Right? So what's the slope from there to there? Well, it's... Oh, no. We did all the way from the top to the bottom. So the bottom is negative 9.8 and negative 1. So negative 9.8 joules minus 19.6 joules over negative 1 meters minus 2 meters. What do you get? You get negative 9.8 joules per meter as the slope. What do you think joules per meter becomes?
Newton meters.
Newtons. Why is it newtons? Because one joule is 1 newton times meter, right? So if you go newtons times meters divided by meters, you get newtons. Therefore, the gravitational force is exactly as predicted. All right? How did we predict it? Because we just took the slope, the slope of du divided by dr, and stuck a negative sign in front of it. Why the negative sign?
Because it's working downwards.
Because it points down, not up. Does that make sense?
Yes.
Gravity always points down. The forces always point down. All right. Now, what if we wanted to derive... what if we wanted to derive that? Well, what you could do... shoot, do I really want to go here? This derivation's a little bit weird. Yeah, that's okay. Let's do it. Yeah, I think you might have to do it later anyway, so we'll take a look at it. So, what's the definition of work from yesterday? Do you guys remember? Work is FD cosine theta, but that's if the theta is constant. Do you remember the more general one? If work is a dot product, it is a line integral. You have to integrate all the little itty bits and bits of work all along the path, right? And add them all up. And you do that with an integral sign. So integral of f dot dr. Yeah. The work due to any given force is equal to the integral of that force dot the path that it takes. All right? But basically what that's saying, in its simpler form, if you want to do a little bit of work, you just take the little bit of distance and dot it with that little bit of force. Agree? Yeah. And that gives you a little bitty bit of change in potential energy. And if you start here and you end there, which we did with the water bottle, right? If I did 9.8 joules of work, what did gravity do? Negative 9.8, so they're opposite of each other, right? So the applied work due to the applied force is equal to negative work due to gravity. And negative work due to gravity is negative force due to gravity dot dr. that means the force due to gravity has got to be equal to du over dr with a negative sign.
How can you just put the dr on the bottom if that was a dot product? Like the dot product?
Oh, yeah, right. How can you just do that? So dot product is those two vectors multiplied times each other, right? Yeah, that's a little sloppy, isn't it? This should be, that dot product should have gone away right there because of this statement right here. Opposite direction. This should just be f times dr and fg times dr. Because of the change in direction, the negative sign came about because of the motion versus the direction of motion versus the direction of the force. I got sloppy. I probably ought to fix my notes. Or
The magnitudes times the angle between the.
cosine the angle.
Oh, you were just writing it easier.
Yeah. All right. Okay. Here's the more important stuff. Potential energy graphs. This is the one that's going to show up on AP multiple choice big time. All right? Every year there's a handful of questions that look like this. Here it goes. Since force is related to potential energy, there's a whole bunch of problems that come out of this. And they come out in every single unit, basically, from here out. Anytime there's a potential energy involved, they're going to ask you to relate that to force somehow. So, for example, if you had a potential energy graph that looks like this, it's this weird kind of inverted hyperbola looking thing. All right? It's got a vertical asymptote and it's got a horizontal asymptote. And the equation for this line was given by u equals negative GMM over r. What's r? Distance this way. And what's u? Potential energy. And it's negative the whole time. All right? That's a hyperbola, right? Okay. How do you get the force from this equation? What do? Take the derivative of that equation. Everybody do that real fast. What do you get? Of negative GMM over r. Take the derivative of it. With respect to r. Because it's negative du over dr, right?
Yeah. Negative
So what's the derivative of this?
GMM over r squared.
GMM over r squared? Well, yeah, but the negative canceled.
Yeah.
Because it's negative du over dr. What's it come out to be? Have you ever heard of this one before? What's that the equation for?
Gravitational force.
That's Newton's law of gravity. So it turns out if that's Newton's law of gravity telling you what the force due to gravity between two planets is, what's this one right here?
It's the
Potential.
energy.
That's the gravitational potential energy that you guys were asking me about yesterday. Negative GMM over R.
Why don't you add the masses together? Why are they multiplying each other?
We're talking between two planets. Planet 1 and Planet 2. Or Earth and Sun. One of these masses is Earth. One of these masses is Sun. What's R? Distance between them. What's big G? Gravitational constant. Why is it negative?
Because each one is pointing towards each other.
Because the force... Why is it negative?
Force
Because it has to be negative in order for the force to be attractive. Because what's downhill on this little line right here? Toward or away? toward. One planet has to be coming towards in order for it to be downhill. Does that make sense? Yes.
I thought the potential energy was just GM over R, because isn't it just like potential energy from one planet? It doesn't matter what else it just.
No, it'd be the potential energy between.
Because it doesn't just matter what the.
You're thinking of gravitational potential, not gravitational potential energy. All right, you're thinking there's a potential field around a planet, but if you stick there's a gravitational potential field around the sun. In other words, a force field around the sun, which doesn't really mean anything until you stick a planet near the sun. And when you do stick a planet near the sun, that planet now has gravitational potential energy.
Just like electricity.
Just like with electricity, right. All right. So, lastly, law of conservation of energy. What's the law of conservation of energy say?
Energy is not
Energy is neither created nor destroyed. It can only change form. Now, imagine I had a box, and here's my box. It's an imaginary box. It's about this big. Can you see it? Good.
created.
Inside the box is a little roller coaster. Little toy roller coaster. And say the little toy roller coaster car starts here and then goes and then around a loop-de-loop and then the back and down to the bottom of the roller coaster. What's true about the total energy in the box? Stayed the same. But did all the energy forms in the box stay the same?
No.
No, because inside the box, that toy roller coaster converted potential energy into kinetic energy, right? But assuming we kept the box closed and away from all heat sources and any heat transfer in and out and any mass transfer in and out, the total amount of energy in the box was the same. Agree? That's the law of conservation of energy. As long as you have a closed, isolated system, the total energy inside the system can't change. It can only turn from one form to another. All right? And you're used to this mathematically with this equation. The total energy before equals the total energy after. All right? If there is no friction or heat or anything like that, we say the total mechanical energy is the same, which means the kinetic plus the potential equals the kinetic plus the potential. And you guys have all done a lot of problems on these. You're going to get a lot more on the homework. I'm going to leave you to it. Nice job today, guys.